Okay, I was telling that some terminology we should learn today. Fine. How many of the students are there? Okay, you are already 32. Good. So, yeah, this is the one actually. Still it is there in your folder. Yeah, it is there in your folder as well. Okay. Okay. I will save this also with the 2013 version. In your, students, shall I start now? All are here, right? 41. Okay, fine. Everybody is listening, right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So today, hope you remember the last class content. We were talking about the minimization. We were talking about I use some other slide. We were discussing about the energy minimization condition, and we were talking about the steep. What is that? What was the last class? This one I used. Okay. This is the one I used for you last class. Optimization techniques we saw, and I was explaining this, and energy minimization, I was explaining the conditions. And I said, like, we have to see some more terminologies, right? So, I will skip, I will post put this. Come on, why are you looking at it?
Ma'am, actually, he is a student who joined from this semester. Like he discontinued before, so I don't think he's added in the classroom.
Oh, who is the guy?
Ma'am, Subhashish, he's in our intake.
Hello, ma'am.
Yeah, can you show me your face?
Oh, wait just a sec.
Okay, how are you?
I'm fine. How are you?
Yeah, fine. So you this time you registered, right?
Yeah, I registered.
But we already finished unit 1.
Yeah, I was attending the classes.
Okay, fine.
Yeah. Yeah, okay,
Okay.
so you just need to add me to the classroom, like Google
Okay,
Class.
can you text me your email now?
Yeah, I am doing it.
No. You text me your email in chat box. Where is he now? Hello. Avinash.
Yes, ma'am.
Avinash.
Yes, ma'am.
What happened? Why you are asking permission? Your email is not added?
No, ma'am. I think added, ma'am.
Then why it is asking permission?
I don't know. Several classes that I think it asking.
Subhashish, now you get the link, okay?
Yeah, yeah. Thank you.
Yeah, I can add it. Okay, fine. Let's start the class now. Yeah. So in the last class, we have seen the methodology that we are going to use for the optimization, but some terminology in the books, it is very essential. I just want to redo it. Probably the same content you already learned it, but this is like I copy pasted the content from the one of the MD book. Okay, so some terminology you should know. That's what it is here, and whatever we learned now, I'll simply give a read. Okay. So from the next class onwards, after Diwali, we will start the unit 2. Unit 3 MD. Okay. So now, the optimization process, I was explaining this graph, right? What graph? So I was explaining this graph, right? So now there is certain terminology, because if I say these are all the concentric circles, that is the what is that very very thin slice of the potential energy. First, we can have a grid kind of representation. So let's see how we can this one. Yeah. So when I say this multivariable optimization algorithms, okay, so what is the meaning of this here? Like, yeah, I have to use simultaneous others, right? Okay, so here we are taking an optimization technique where to find out what is the least energy or the saddle point or whatever, right? So what happens is, suppose you have a potential energy surface which has a multivariable. What is this variable? This side you will have one variable, this side you will have a one variable, and this side you will have a one variable. If this is a Cartesian coordinates, okay? So this has a 3 degrees of freedom: x direction, y direction, and the z direction. Suppose if you are plotting this in another like momentum phase. What is the momentum phase? I always explain. The momentum phase is the one where we are including so when we have x, y, and z, this is a normal Cartesian coordinate. So if you include the momentum in the x direction, the momentum in the y direction, and the momentum in the z direction, it's a phase space. All put together, we say it's a phase space. Okay. So what happens is you can have a precise definition or description of a system either in a 3-dimensional way or in a 6-dimensional way, that according to the problem, the necessity of the problem. But we have to identify what is really the essential coordinate that is describing the features very perfectly. So whatever we are saying, in the sense, every time when we are going with a potential energy surface, it is a surface generated by multivariable. So if requires, we have to optimize all the multivariables also. So optimization problems which when come across in molecular modeling are problems. where the objective functions have more than a single variable on which a given function depends on. Suppose if I say this is equal to y is equal to mx1 plus mx2 plus c, means one function is there which is varying according to x1 and x2. So let's see, this is an example. F of x is equal to this for rough estimate, example I'm giving x1 square plus x2 square, just to tell you that this function is dependent on x1. This function is also dependent on x2. So x1 is equal to 0. If you put this value, you can have a solution for this. But the variable, the x1, from where it starts, the range of x1, the range of x2 gives the surface. This function can be represented by a surface. We have to find out the minimum value of the function and what values of x and x2 is the minimum value at time. So now, what is the condition? Like we have to go with the condition. The condition to identify the first derivative is 0 and the second derivative should be greater than 0. This is for the minimum value. For the maximum, the second derivative should be greater than, less than 0. Okay, so you have to go with the optimization value and identify, okay, what could be the characteristic, whether this is a minimum or this is a saddle point or this is a maximum, whatever it is. So in a way, we will be having a multivariable surface where we can take our own analysis either in the x1 direction or in the y1 direction, x2 direction. How we can take the partial derivative. Okay, so the only difference in the definite differential and the partial derivative is, suppose your function is having x, y, and z. Okay, and you want to take a definite differential is d by d x comma y comma z, means you can take a function with respect to dx plus df by dy plus df by dz. Okay, so the differentiation includes all the variables. But if you are going with the, what is this? If you are going with the partial derivative, if you worry only about x, if your choice is only x, or if your choice is only y, what happens? You can go with a partial derivative of, suppose if it is only with respect to x, you can go with dou f by dou x. So if x is the reaction coordinate, understand? If x is the only essential variable which defines the entire phenomena, you can consider the x as the reaction coordinate and take a dou f by dou x. Otherwise, if y is the reaction coordinate, you should take dou f by dou y. If z is the one, you should take dou f by dou z. That is our choice. So this is a multivariable system that you have to choose it. Then I'm going to use certain terminology, level sets, level curves, and the gradients. What is this? Now, you see this picture, I'm coming back to this. The function values under study are represented as a contour maps. What is this? Whatever this put, we say it's a contour maps. Only two I have put, but you can draw more concentric circles in this picture, with their circles representing each function value. That is, the circle is one f of x, the same f of x with a different variable value. So the variable only defines the population of the concentric circle, because that is what, like I show you this picture. So this concentric circle is the function with a particular variable value, the same function with a different variable value. So every level set, okay, that describes the function but the variable value. Understand? So now I'm going to read the same. The function values under study are represented as contour maps with the circles representing each function value. Any function f of x. Suppose you are solving, this is a function and you are solving this, that is talking about one level set. So this is one level set, this is another level set, which is a set of points having the same height. See, this circle is a set of points having the same height. How? This circle having that particular, this is the same height in the potential energy surface. That means like you can come this way, cut any time. So that is having about potential energy one level. The height is the same. So what is the meaning? Every concentric circle is talking about one particular potential energy. Okay. You all understand what I'm trying to convey? Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So any function is a level set and which is a set of points having the same height in the potential energy surface. These contours are called as level sets or level curves. So the terminology we are going to use the concentric circle which is at the same height in the potential energy surface is called at the level set or level curves. So any point on the circle or the curve, the function value will be same, correct? So we are simply cutting that cross section. So the same function value. That is what we put it as a C. It is not a variable. In the level set, it is only one value. The outermost contour will have a highest function value and the innermost circle progressively have a smaller value. How? Because if you come here, so this one function outermost, and if you come down minimum, it should have a lowest energy. So this is the highest, lowest, 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 so it is a lowest. Whereas if you are going to a saddle point, it is the energy is increasing. That is the maximum. That is different. Now let us find out this characterization. So at the bottommost point, the function will have zero values and it is said to be the minimum at the point. So now you will come here, this is almost the zero. There is no variation in all the variables. So that is the minimum point. At each point on the curve, there are gradients given by delta F. What is the delta F? This is dou F by dou X. Why it is a gradient? So if I say, if in a graph, okay, this is the X, this is the Y. So I am putting one graph. Okay, so what happened? I am interested in particular point. Okay, I want to find out a tangent. I don't know. It should be a tangent. Okay, so this is the tangent at a particular point. What happens? I want to understand the slope. Tangent is the name for the gradient. Gradient is the variation. How I calculate, okay, this particular point. Suppose like I'm in one particular region I'm focusing on. I want to understand the variation. So what I do? Oh my God. I draw a line for the X range. I draw a line for the Y range. Who is this? Nobody. Okay. So what I should take? If I take dy, the change in the y divided by the change in the x, that talks about the gradient or that talks about the tangent. You all agree? Okay, so now I am coming back to this. So every point, if you want to understand the tangent, why you want to understand the tangent? Because if the tangent gradient is positive, it is increasing. If the tangent is negative, it is decreasing. So our function to come down, so we have to look for the gradient. If the function expresses gradient in the negative scale, we understand that, okay, we were here, now the gradient is negative. So the new point is coming down. This is our assumption. Suppose, like this is easy for you to move down to understand what is the least one. If this comes here, will there be any change in dy by dx? No. It is only one exact point where your gradient is equal to 0. Okay. So initially will come negative, negative, then the increment will be 0. So at this point, the gradients given by this point in the steepest direction. The direction of the steepest descent is given by minus f of x. Why it is minus? Because our function, we have to come down. We are looking for the downhill. So which we get by searching in the opposite direction. Normally we take this gradient and we take the negative. So whatever like your quantum, the gradient change you understand, the delta change after you identify the delta change, if you subtract, then this will follow in the reverse direction. What does it mean? Okay, so this is your dy by dx. You understood this. If you take the difference and add it, then the point will come here. And if you take the difference and subtract, then the point will come here. This is the simple meaning. Understand? So you understand a dy by dx in a general way, and you subtract it, then you will come down to the lower hill. If you add it, you will go to the upper hill. Daddy, 10:30 to 11:30 class நான் அப்புறம் பேசுறேன். Okay, so that is what we have to move in the reverse direction. So I will read the sentence again. At the bottommost point, the function will have 0 value and it is said to be the minimum at that point. At each point on the curve, there are gradients, definitely, because otherwise, why it is a gradient? There are gradients. It is again another physics. See, when I calculate the difference, it is very minimum. No. When I calculate the difference, it is there but little bit minimum. But the difference is increasing. If there is a steepest increase, the difference is more. Here, the difference is less. Okay. So, throughout this curve, you can see the variation in the gradients itself. You can see the variation in dy by dx itself. That is a sentence. It is not a simple sentence. So, at the bottommost point, the function will have 0 value and it is said to be the minimum at the point. At each point on the curve, there are gradients given by delta f of x, pointing to the steepest direction. The direction of the steepest descent, we have to come down. We are not getting up. So descent means we have to put it by minus. We have to step down, which we get by searching in the opposite direction. Opposite direction of delta of f of x. That is minus delta f of x. The contour map is a vector field because this has a directional property. According to the direction only we are moving, with the gradients at every point. The gradients are always tangent to the level surface. So, what I explained here, gradient is always a tangent. Okay, if I say gradient also same, tangent also same. This is the meaning. The contour map is a vector field with a gradient at every point. The gradients are always tangent to the level surface. There's a plane tangent to the point and the gradient will always be orthogonal to the plane. The maximum and minimum point in the contour maps, let us ignore that. Maximum and minimum we can characterize according to the condition what I give you here. There's a minimum. I think in the previous slide I told you that we have conditions for minimum, maximum and saddle points. Okay. Now the same we explained. Contours, it is already there, the optimality criteria. Yeah, as it is given in the book. For one example, optimality criteria is optimization. What is that? The first partial derivative will be a, what is that? That how they are deriving Taylor series, I think. Yeah, I didn't explain this Taylor series, right? Did I explain? Anybody? Students? Hello?
Yes, ma'am.
Okay, so the problem is like the whatever I explained before, that is we are talking about the delta f of x and we have to take out the partial derivative. If it is a multivariable x1 square, x2 square, so we have to take dou f by x1 and dou f by dou x2. So this will be reduced as a solution. So every time when we are going with the first derivative, then the second derivative you have to choose it. For the first order partial derivatives are calculated using the central difference. Okay, this is not a matter because these guys are like typically from the book. So you don't worry because delta, normally delta square f of x is defined to be positive definitive if for any point y in the search direction which is greater than 0. That will talk about, I think, eigenvalue decomposition and all, it is not required, but you can study the same from here. So this is the condition. You only go with this. Let us not read it. That will be giving a confusion. So you keep this in mind. The first order derivative will be 0. And okay, in the second order derivative, if it is greater than 0, okay, for all the variables, okay, for everything, x square as well as y square. This is the minimum. But in the saddle point, at least one, we have to understand the saddle point, we have to identify the reaction coordinate. What does it mean? One particular variable, you will have m less than 0. Okay. So this 1 second derivative is negative and all other second derivatives are positive. If this is the condition, this is the saddle point. Okay. So what happened? So here you see everything is greater than 0. Only one particular reaction coordinate is less than 0. Less than 0 is the maximum deriving reaction coordinate. Okay. So this is the condition and let us not go and stuck your mind. Okay. This is the unidirectional search. And in the last class, like I was using the slide to talk about. Yes. Conjugate gradient, and we were talking about the movement in one particular direction. Okay, so I think the conjugate gradient only. Okay. Why we say it's a unidirectional search? Because our movement from outside to inside is one direction only. It cannot go with a multiple directions. So the successive unidirectional search along each component of the vector to find the minimum along the search direction. That is what we say it's a unidirectional search. It is one-dimensional search performed by comparing the function values along a specific direction. The search is performed for a point x of t and along a search direction now s of t. So every increment, this is the old value and will be getting a new value according to the search direction. So you will have passing through the xt and orienting along the x direction you will be moving. So the derivative of this function is called a directional derivative because every time you are taking a gradient according to one particular direction, so it's a directional derivative. So you will be getting the new value of x from the previous value of x using the directional property. So alpha is a scalar quantity which specifies the distance of x of alpha from the old point x of t. And x alpha is a vector specifying all the design variables of xi alpha. What is that? Alpha can be positive or negative because According to the search direction, it can be positive or negative. And if you are going to the saddle point, you have to take the minimum, you have to take the negative. So it is one directional space. That's what we say. It's a unidirectional space. See, we have seen everything in the last class, but I'm simply using the terminologies. Why we are saying it's a unidirectional search. Finding the minimum, the same, this one you can use it. No need to write that one, but for your understanding only I have given it. I think nothing more. I think there is one slide which talks about the advantage. I think this the last class I explained. Yes. So I explained, right, in the first minimization process, in the first half of the minimization program, you have to use the steepest descent. And in the second half of the minimization process, you have to use the conjugate gradient. Okay. So all put together, the unit 2 is getting over now. So when are you writing? When will you write this unit 2 internal? After Diwali, Monday. Is that fine? Coming Monday, you will be writing the unit 2 as a test, internal test. Students?
Okay, ma'am.
Okay, ma'am.
Okay, ma'am.
Actually, I forgot to post your thing that I should do it now. Who did this? Did I send any other material in PS? No, no. Wait. Post it only. This material.
Please everyone fill your attendance.
What?
Ma'am, I told to everyone to fill your attendance.
Yeah. Anything is missing in my unit 1 class. I didn't post it. Did I post this PPT? Anyway, I can remove. I didn't do it right now. Oh, MD lecture is there. MD, what's this one? Okay. Anything else? So I think today from next class onwards we'll be seeing this molecular dynamic simulations. So everybody send your assignment?
Yes, ma'am.
Yes, ma'am.
Okay. Anybody who has not sent it now, until now? Is there anybody? No. Okay. So have a great day. Enjoy your Diwali in a safe mode, and we'll see you after Diwali. Okay?
Happy Diwali, ma'am.
Okay, ma. Okay, ma. So happy Diwali to you all. Yeah.